Hi guys, can I get a sound check?
I can hear you, Professor.
Okay, great.
How you doing, Professor?
Good, thanks. Sorry, I'm behind the curve here. I was answering questions in my previous class. Oops. So while I'm doing this, any questions on the project? Do you guys want to get started with? Everybody's feeling solid on the project, or nobody started yet? I think some of you guys have started. Okay, let's see, where were we at? So, here we were. Nice. Okay, so no questions, guys, on the project. Any feelings? Any thoughts?
I just had a quick question regarding like due date. So I think like once you mentioned Tuesday and another day, like you mentioned it was due Thursday. When should we expect to turn this in?
It doesn't matter to me. If you guys need another couple of days, it's fine. We can make it Thursday. Did I put something on did I put anything on an announcements?
I'm not sure, but I know you mentioned it in your lecture.
Okay, I will, if I did put it on the announcement, I'll change it so we can make it Thursday.
All right, thank you.
Sure. Give you guys a little bit of time. Cool. All right, let's see, where were we? Sorry, guys. Slide deck. Good notes. No. All right, okay. Where were we? Okay, so guys, where we left it last time is we were coming up with a hand sort of estimation. Sorry, let me just put chat questions. On the font it says Tuesday, I'm pretty sure, but Thursday works for me. Okay, great. Yeah, I think I probably on the announcements, I think I had put in Tuesday. So I'll just go ahead and change that to make sure, nobody gets confused. Okay, so back to the lecture. So, we're doing these, estimations on the delay of a CMOS inverter. And basically, the model that we used for this delay is that the input is, a infinitely fast, step function from 0 to VDD. So here, and what happens on the output is, the output transitions. We talked about what happens, say in this case, we're just looking at the NMOS turning on. So when you go from 0 to VDD, the PMOS just turns off. Okay, that one's easy. But then the NMOS goes through both saturation and linear modes of operation. So it makes things a little complicated, because initially, because the because the output is high, a high value. The reason that the output is a high value is previously the input was 0, the PMOS was on, and it made the output high. So when the input goes to VDD, initially the output voltage is high, so there's a large drain source voltage across the NMOS. it turns on, but because it has a large drain source voltage, it's going to be in saturated operating mode. And in a saturated operating mode, because there's no VDS component in the equation for that. So there's no VDS current component. It just looks like a current source. And a current source discharging a capacitor just looks like a kind of a straight line. So initially you get this straight line response. And then at some point, the VDS of this guy shrinks enough that the NMOS goes into linear mode of operation. And then it looks like a very bad nonlinear resistor, because now it is a function of VDS, is now in the equation for ID. So it looks like a sort of exponential characteristic of like your typical RC sort of time constant fall until it goes to zero. Okay, so it goes through these two modes of operation. Okay, so if we look at kind of, I was making a very kind drawing here. So it kind of looks like this is maybe a more realistic drawing. So, and the reason it ends up being more realistic is, first I'll just, you guys will see it as you're doing it in a project, what the waveforms look like. But so when I forgot what I said in the project in terms of the rise time of the input, but in this case, notice that the input is not going up infinitely fast. So this is probably this VN. In all probability, VN is already being generated from another CMOS inverter, because notice, one, it's not like a straight up, straight down waveform. So there's a certain rise fall times already. And it's got these two components, which don't look like, perfect straight line and exponential, but somewhat. So you can kind of see this is sort of the straight line portion, and this is the exponential portion. And this is on the fall side. So you get kind of the straight line portion, and then it goes into the linear operation, and you get this exponential function so this is if something is driving VN. And then VN is driving V out, you kind of get this straight line and then exponential, sort of a straight line and exponential. So that's why these waveforms, as you'll see in your project, look like that. But so that's one thing to point out. But then the main thing I wanted to point out from this graph is what are definitions of transient behavior, of timing. So we have, I think I talked about this a little bit, maybe a couple of lectures ago, talking about project one, because you needed to know it for that. But basically you have a couple of things. You need to know the propagation delay. So when you're looking at something like this, so let's just say, this is VN, this is V out. So we're always talking about this inverter here, okay? So the propagation delay, prop delay, is from in to out, okay? So the prop delay is the delay between the 50% point of the input in transition to the 50% of the output in transition. So the prop delay is from input to output, and it's a different number depending on whether the output is falling or the output is rising. So when the output is falling, you call it the prop delay fall, or TPDF. Okay, so by definition, because an inverter, it means the input's rising at that point. So it's from the 50% point here to the 50% point here. If this was let's say if it was a 1.8 volt process or a 0.18 micron process like we have in our class, then Vn would go from 0 to 1.8 volts, and the 50% point would be 0.9 volts. It wouldn't be 0.5 volts. So it'd start from 0.9 volts on the input to 0.9 volts on the output. So you'd have a prop delay rise. Sorry, this is a prop delay fall, and then you'd have a prop delay rise. And depending on what you're asked, sometimes somebody asks for like a prop delay and you can do an average prop delay. So if there's no distinction between rise and fall, it's probably like the average value. Okay, so that's prop delay. And then you also have the rise and fall, okay, which is just on the output itself. So now you're not talking about the input changing. And those are defined either from the 10% to 90%, or in this case, it's from 20% to 80%. There's no standard, but it's usually one of those. So it goes from 0.8 VDD, or the 80% point of the signal, to when it's to 20% of the value, and that'll be the fall time. And the rise time is the inverse, from 20% to 80%. Okay, would be the rise time. So those are the delay definitions, okay? So there's a couple of other delay definitions that may not make sense to you right now, but they'll come back to haunt us when we get into sequential circuits. And that is contamination delay, okay? Now, most of the time, God, for years and years and years, all I would hear about is propagation delay or prop delay. I don't know, I guess I should probably it would be great to do a survey of the class sometime to see who's heard of prop delay and who's heard of contamination delay. God knows I hadn't heard of contamination delay for a very long time. The difference is that, in an inverter, okay, in an inverter, they're the same, right? There's no difference between prop delay and contamination delay. Prop delay is the worst case delay. So it is, so this is, prop delay is the longest delay from V in to V out. And contamination delay, I don't know why it's called contamination delay, is the shortest delay from V in to V out. So again, in a case like an inverter, it doesn't quite make sense that you would have two values, because it's just the delay, right? And there's just, you get a delay from input to output, and there's no shortest or longest. But think of the case of a NAND gate, for example. So how do I draw this so that it is not, this is going to make a really complicated drawing, but say you have a situation where you're going from the output your output is going low, right? Someone just draw that. Sorry guys, I might do this in a couple of iterations because I'm doing it on the fly here, but so the output is going from high to low. So this is out E, and this is time. So there's only one way your output can go from high to low, and that is if both A and B turn on together. Otherwise, if only A turns on or B turns on, the output is not going to transition to low. Okay, so there's only one way you can get a low. So no matter what there's only one way you can do that is when A and B are both on. Okay, so if they're both high, if this is high and this is high, you get an output low going transition. But remember that there is 3 ways where the output can make a high going transition. So case 1 is when both A and B go low. So I'm going to just draw that kind of randomly. So A and B go to 0. Okay. In that case, you have both of these guys turning on at the same time and pulling on this capacitance, pulling this point up. So basically you get a lot of current, okay? As much current as 2 of these guys can handle. But let's say you only have A go to 0 and B stays high, okay? In that case, you're going to get a longer transition time. Okay, so that's when A goes to 0 and B just stays 1. Okay, that's a legitimate way to go from low to high, but only A turns on, and you won't get the benefit of the current through B, the PMOS transistor with B on its gate. Boy, I really did a bad job of drawing this. So it ends up being significantly slower. And in fact, if the other thing happens, so this is or B goes to 0 and A is 1. Okay, in either case, you just have one or the other one turning on. So you get a slower transition. So what happens is, what it looks like is, this guy, your falling delay, your prop delay and contamination delay are exactly the same thing because there's only one way to get it. But when you're talking about rise time or this rising transition, you get this guy would be your contamination delay. It'd be the fastest transition from low to high. So you'd get a contamination delay rise. So this would be, write this down. So T contamination delay fall is T prop delay fall. But here, this would be T contamination delay rise, and this guy would be T prop delay rise. So the longer transition is called prop delay, and the shorter transition is called contamination delay, the faster transition from, and these are just we're not talking about rise fall times. We're just talking about propagation delay. So from input to output. Okay. So the next level, even when I saw this initially, I was like, well, I almost, you only want to, why would you ever worry about contamination delay? I usually worry about delays being too long and not too short, right? Because, long delays means takes stuff longer. You gotta, you're gonna increase your clock periods or, reduce your clock frequency, things slow down. That's what I worry about because everybody always wants to go fast, obviously. And so who cares about contamination delay? The reason we worry about contamination delay is, as we'll see in the sequential circuit, once we get past these are the combinational circuits, inverters, NAND gates, etc. The sequential circuits are latches, flip-flops, etc. And then when you get to the flip-flops, if signals get there, you could have a situation where a signal, just if you have a short enough of number of components, number of combinational components between 2 flip-flop stages, if that delay is too short, you're going to get a hold violation. Okay, and a hold violation means that the signal goes straight through the two flip-flops in one shot, in one sort of clock edge, and it's going to be like death. And a hold time violation is really death of your circuit. There's nothing you can do to bring that circuit back to life. You can't slow down the clock, nothing, because it's, one clock edge is the data is going through in one clock edge. So even if you slow down the clock, doesn't matter. It's like that it's going to go through in that one edge. It's not a edge to edge type of thing that you can slow down. You could, if you have a setup violation, you get setup and hold time violations in flip-flop circuits. Setup violations, you can actually increase your clock length, the period of your clock, and recover from it. It won't be great news because you won't meet your spec, but at least you get a working device that you can do something with. If you end up with a hold violation, you're just, there's nothing you can do. You're just screwed. So this contamination delay is very dangerous for this hold time violation, because if you don't have a lot of stages, you're under threat of being in this hold time violation. You could be also in a situation that you have to consider what is the fastest transition through these few number of combinational circuits. And so anyway, this contamination delay will later on, again, in the sequential circuit part, we'll see how it's kind of a scary thing. Something you do have to keep a eye on. All right. Okay. So what I want to say here.
Professor?
Yeah.
I had a question about the delays. Like, is there a feature on LTSpice where it can like generate the numbers for the delays so that we wouldn't have to like look into our output graph?
Yeah, you Sophia, you broke up a bit, but so let me repeat your question, make sure I heard it correctly. You were asking, is there some kind of a function in Spice that would sort of automatically read out the value of delays, etc.?
Yes.
So if you look into it, there's something called a dot measure statement, dot measure. And so, if you pop up the, LTSpice help, or just go on the web and look like for dot measure statements, and for Spice, you can use it to measure all sorts of stuff. And so there's a little bit of a setup involved. There is a chapter in your book. Let me just give me 1 second. Let me pop up the book here. 3. So a good chapter, by the way, generally for project 1 or just simulation is chapter 8. It's called Circuit Simulation. Sort of goes through, it talks about Spice and how it works, etc. I thought it had some example of dot measure statements. Let me see if I see it. Yeah. So if you go, I don't know if you have the book in front of you, Sophia, or the rest of you guys. If you go to page 296, you will see there's a Spice deck there. It's a sort of, I don't know what the Spice deck is doing, but anyway, Spice deck there, and it says it's figure 8.10, and it's got a bunch. It's like shows you how to do the measure statement for prop delay rise, prop delay fall, T rise, T fall, and so on. So it's definitely a good way to go. I mean, you got to be a little careful, just as usual, make sure you debug it, make sure you don't have garbage in, garbage out. So hopefully that helped. I don't know if you have the book in front of you, but anyway.
Yeah, thank you.
Sure.
Professor,
Yeah.
for the project part, do you expect us to show the delay also, if there is any?
Yeah, so let's see. Where are we? Just give me a second. I said yeah with a lot of confidence, but in fact, my memory is not good. So let me just go check it out. Yeah, so on project 1, so problem 2 is just a DC transfer function, but problem 3 is the delay. And so for that delay, I'm asking, so if you look at the project, problem 3E, it says plot and state your prop delay rise, prop delay fall, T rise and T fall numbers.
Okay.
Yeah. So there's sort of 4 things you have to do for that project, for the problem. Okay, let's see where we're. Any other questions, guys, about that, about the projects? Nope. Okay. Okay, so what does this all mean? Sort of coming back to all this. If you really want to calculate the delay, you can just run a SPICE simulation, right? That's kind of what we're doing. This, again, over and over again, this is the philosophy of what we're doing in this class. And so it's worth repeating, because sometimes it gets really confusing about what we're doing here. So to actually get the delay of a circuit you're designing, so this is the circuit, okay? In this case, it's just an inverter. You put it together and you actually simulate in SPICE, and you're going to get, that's as accurate as you're going to get, right? But that's, we're doing that in parallel with what we're doing, but this methodology that we're going to talk about now is intended to get us a rough order of magnitude or an estimate of the delay. Now, why is that? Where is that helpful? Well, it's helpful, as you will sort of build up on it over time. It's helpful because a lot of times, especially at the beginning of the project, you don't know what you're going to design, right? So you and the team, management, the customer, guys are talking about the functionality you're going to have. You're going to have like a rough idea of what the logic gates may look like. You've got a target process in mind. So in those kind of situations, it's really helpful to have a sort of, you want to call it back of the envelope, an estimation approach to calculating the delay, because you don't have the circuit yet. If you actually go design the circuit, it's going to take you weeks, months to design that particular circuit, simulate it. And then at that point, you'll go, oh, I'm not going to meet this, this circuit is not going to meet this clock speed in this process, right? And months have gone by at that point. And now you have to go back to your customer, go back to the team, go back to the management and say, hey guys, nope, we need to either change some functionality, change the layering of the circuit, or target a faster process. But by that point, months have gone by. What you want to do is do a lot of estimations, like, that's where you're working with Excel sheets, you're doing with back of the envelope estimations, et cetera, hand calculations, to make sure you're kind of in the right you're in the right ballpark, because if you've already designed your circuits, or you're designing it enough that you're actually doing like SPICE simulations or logic simulations, by then if you're going down the wrong track, it's we saw one of the first few lectures we had was on the cost of developing a circuit, and you guys saw how expensive the non-recurring engineering expense of the circuit was. And a lot of that is the amount of time you spend in your design. So by then you would have wasted a lot of cost that either your company or the customer has to incur. So that's really bad. That becomes additional NRE for your project. And if you have to change the specifications to the circuit, or say the clock rate or something like that, then either your customer or the marketing people in your company, they have to go back and check, hey, is this going to still be like a usable product? Is this acceptable to the end customer? And or if you want to sort of go, no, we need to hit the speed, you need to probably target a tighter process, which is going to increase your NRE further, and or increase the per piece price for your product. And then again, you'll have to go and recalculate, hey, like, is this still make sense? At this new price point, will people still be interested? So long story short, there's a place to do simulations, detailed simulations, but there is definitely a place, and usually it's at the very beginning of a project, where you want to do these, Excel level, hand level calculations to get a rough idea of like how things look. Are you on the, you're going in the right direction, and get some insight into why not, or why yes, etc. So that's a very typical place. Another typical place for hand calculations is, God forbid, you're sitting in the lab after the chips come back and something's not working, right? Something's not working. Nobody knows why. So again, when you're debugging, I don't know how much debug experience you guys have had sitting in the lab, but whether it's a chip, whether it's code, whether it's something else, a lot of times the same story you're doing in your mind. You're doing a lot of different if then, like, well, maybe it's this, maybe it's that. Let me poke here, let me poke there. But it would be too cumbersome if every guess you had sitting in the lab. Now imagine you're just sitting in a lab in front of your instruments and stuff and your chip. You want to do like sort of quick hand calculations, because to go fire up your SPICE simulations, and you got to spend a day or two simulating stuff for every hunch that you have, is also too cumbersome. So those are the two places at the beginning of the project, and while you're debugging your chip, etc., that's really handy to have these kind of simple models in your hand, and to kind of see where you're at. So that's where we're going now, is doing these delay estimations. Okay, and the primary technique of this delay estimation is it turns out that if you model your transistor, so remember that the transistor in reality, it's doing some pretty complicated things, right? It's going from being off, just for the sake of discussion, let's say we're talking about the NMOS transistor here, pulling down. It's going from off to saturation to, at some point, it goes to linear and so on. So there's a lot of equations, a lot of things to keep track of, and that's what SPICE is doing. But it turns out that, do I have a graph of this somewhere? Nope, should have put in a graph. Yeah, it's kind of hard to persuade you guys, but trust me, is that the graphs are in the book. But if you just model the transistor, so let's say the N MOSFET, if I just model that as a resistor, okay, so basically what I have is, so if I model this guy as a resistor and a capacitor, it makes a pretty good model of what happens. So let me get more, let me see actually if I can show this to you guys, because it's hard to, I should have plotted it out. Here's a good, whoops. Doing this. Just give me 1 second. I'm going to share my screen here, guys. Where is it? Here it is. So you guys, hopefully you guys see this figure 4.4, where on the horizontal axis we have time, and on the vertical axis we have voltage. And what it's doing is it's comparing, so this, you guys see that, figure 4.4?
Yeah, we see it.
Yeah, okay. So basically you have, this sort of a straight line is this input with, A, which is shift, changing, going from low to high very quickly. And then it's showing various fall times. One of them is, the B is the sort of the SPICE, one of them is the SPICE simulation, I'm sorry. One of them is doing a detailed hand calculations called Shockley of the level 1 model. And then lastly, it gives this RC model. So just replacing the NMOS or PMOS, just replacing the transistor with a simple R and a C. And what that shows is, if you look at them at any particular point, the RC model is not a great match to the SPICE, right? I mean, if I look at any particular model, it's not, especially around, if you look at time of like 50 picoseconds, right? The RC model gives a much higher value than the SPICE model. Not great. So at any one point, it's not great. But if you just did a prop delay calculation, so from the 50% point of input to the 50% point of the output, so that would be, around, I don't know, so around 25, 30 picoseconds sort of time. It's a pretty darn close value between all those three. Okay, so as far as a general estimate of the delay, it's a pretty good estimate. It ends up being a pretty good estimate. If you think of it as like point by point, yeah, it's not great. But again, when you look at the prop delay, it's really close to what you would get in SPICE, this really simple model. And, I don't have a good explanation about like philosophically why that ends up being the case, but it ends up being the case, thankfully. So we can use it as a method to estimate delay. So let me talk about it a little bit more detail. So let me, let's see, I'm going to share anymore. Stop share. Let me just go back to my iPad. So again, so let me say the same thing again, is that if I was going to compare, so you have SPICE. So if this was a fall propagation situation, so this would be SPICE, And this would be my RC. Maybe my RC will look like that. Okay, or whoops, at some point it'll go down here, whatever it is. I'm just making up stuff. So at each one of these points is not, a great estimate. But if, let's say this is at t equal to t0 is when the input transition. So we're looking from here to here, or from the same place to the RC model, it ends up that these two values end up, again, with a real simple RC type of estimate ends up being really close. So like, probably less than 10% of error. So depending on the values of R and C that you pick. Okay, so let me see here. Oops. Okay, so what does this look like? So if you look at, so if I put in, so say I got VDD coming in here, and then I got R sub, I'm going to call these R sub n and C sub n, and you guys will see why. So the transfer function here is 1 over 1, it's just a RC transfer function, which gives you, a V out is VDD exponential minus T over tau, with tau being Rn Cn. Okay, so just a RC sort of a circuit. Okay, so what happens here is we have, but what happens is we have to pick the right R and the right C. Okay, and this comes from it comes from the process. Okay, so let me see if I have, you have a effective resistance. So let's look at that. Let's say if you got a yeah. This is going to get complicated, but you guys don't have to know this, okay? But I'm just saying how you're going to come up with this resistance. Is there something else I want to say? So let me just rewind here. Is if you pick the right value of R and a right value of C, you're going to come up with a pretty good estimate of the delay through a transistor, a MOS transistor. This is my like claim. So, and then the question becomes, what is that value of R and what is that value of C? Okay. First of all, for each process, there is a different value for R and C for an NMOS transistor and for a PMOS transistor. So let's say we're in a, so we are in the 0.18 micron process at TSMC. You're going to end up with a value of R sub n for, this would be the NMOS, sort of what you'd call effective resistance. Effective for doing this or delay estimate. And a C sub n is a NMOS effective capacitance. And again, that these are by effective, these are means these are we can use these for delay calculations. And then you'd have a R sub P and a C sub P, which are for the P MOSFETs. PMOS, R, and C. Now, what does that mean? Well, the way they do it is they go, okay, let's just look at the NMOS. This is going to get a little complicated. You guys don't need to necessarily know this, but just for the sake of completeness, let's say you have, these are the curves for gonna have a bunch of curves for I sub D versus V sub D. Okay, we talked about this in detail. And then this goes from, I don't know, from VDD of 0.5 volts. Okay, sorry, VGS of 0.5 volts. No, wrong. VGS of 0.9 volts, right? Because we want to go from the sort of the prop delay of prop delay is when the input goes with a VGS of 0.9 volts to VGS. What am I want to say here? Sorry, let me think for a second. So if you have an NMOS and it is turning on, the VGS is gonna go from 0.5, right? The VGS is gonna go from 0.9 to 1.8. Okay, because if you look at what happens when we're doing prop delay, the input is, we're looking at the 50% point on the input, and we want to know what happens when the input has like transitioned from this 50% point to the full value, because that's the range of time over which the output is falling. Okay, this is like sort of the business end of the input switching for the output. So that for this amount of time that the output is switching, you're considering what happens when the input is kind of doing this. So you look at VGS going from 0.9 volts to 1.8 volts, okay? And simultaneously, you're looking about what happens when the VDS, which is the output, is going from 1.8 volts to 0.9 volts. Okay, so let's say this is the curve for VGS of 0.9. This is the curve for VGS of 1.8. Okay, so this is what the input's doing. It's sort of shifting through here. Okay, and the output, as that's happening, the output in each one of these cases, it's getting closer to the 50% point of the output. Do you guys kind of see what I'm talking about here? I know it's complicated. So you're going from the range of currents that you'll have goes from here to here. Okay, these are the sort of the permissible points where your input is going from the 50% point to the max, right? Turning on your NMOS, and your output is going from max to 50% point. So to get your prop delay, you're going from this point of current to these are the extremes of your current curve. Okay. Does that make sense? So if nobody said it made sense. I'm just going to assume that silence is compliance or complicity. I don't know what it is. Not compliance, but complicity. Okay. So if I was going to make a resistor, this is like really getting kind of hokey, guys. But if you're going to have a resistor, this is what it would look like. You would say, okay, well, remember, resistor is on a curve like ID versus VDS is going to look like a straight line with value 1 over R. Okay, so on this end, you have a 1 over R1. And on this end, you have a 1 over R2, if you had a resistor. Okay, so what you do is you split the difference and you get an average value of resistance between these two. And it gives you like basically what the current you would end up with at this value of your output. Okay, so remember what you're doing is you're looking at, you have this RC. So this value, you want it to be the value at which sort of like your resistance is giving the same value out here. Okay, for the delay for this guy going to this guy. Boy, I'm really doing a bad job of explaining this. But anyway, so you're doing this really, I guess it's pretty hokey, let's face it, method of coming up with an average resistance that's gonna give you an average effective current for this transition, which is, in reality, you're getting this really complicated transition of your input and your output. And you're saying, okay, if I was gonna estimate that with an effective resistance, I would figure out the resistance here and the effective resistance here. And by resistance, I mean a resistance that would give me this current at this voltage, and a resistance here that would give me this current at this voltage. Then I'm going to average them and think that, while I'm transitioning, I can use that average resistance. Okay. So again, this is very inaccurate to estimate the actual values at any particular point in time, but it ends up being like a pretty good value for hand calculations. So if we go back to the book, again, like you guys, thankfully, you don't have to do this. If we go to the book, I'm going to share it. So the advantage of this is you only have to do it once per process. So let's say you're in the 0.18 micron process. All you need to do is to figure out R sub n once, and you're done. You can use that for all your transistors and gates, etc. So let me show you what it looks like. Let me share my screen. Going back to the book. And again, I think it's, where is it? I mean, the book, the good thing is the book does go through the gory details, but I don't know if I'd do it. So so net, if you go to table 8.5 of your book, it's done this kindly for you so what I highlighted in red here is the TSMC 180 process, which is what we're using, 1.8 volts. And very kindly, these guys, so if you look at, I don't know if you guys can see my cursor. So, this R sub n, which is 2.69 kilo ohm microns, is this average resistance for an NMOS transistor. And there's a R sub P, which is down here, which is 6.5 kilo ohm micron for a PMOS transistor. Now let's talk about that a little bit. Why, we're talking about resistance, so it should be, kilo ohm makes sense, but what's this micron doing? Well, it turns out that as you make a transistor wider, so let's say a 10 micron, in this model, a 10 micron wide transistor has 1/10 the resistance of a 1 micron transistor, because a 10 micron wide transistor has 10 times the output current of a 1 micron wide transistor, given the same voltages, same process, etc., right? Because you have the W over L component in your IDS values. So basically what happens is you end up dividing your resistance by the width, dividing this R sub n by the width of your device. So if you had a 1 micron wide device, the resistance, the R sub n of, the resistance of, the effective resistance of that device would be 2.69 kilo ohm microns divided by 1 micron. So it ended up with 2.69 kilo ohms. If you had a 10 micron wide device, the effective resistance of that would be this divided by 10 microns. So it would end up being 269 ohms. Okay, so that's how you use this value. You just sort of scale it with the width. The wider you get, the lower this resistance. So if you have a big capacitance to drive, you want to go faster within certain limits, as we'll see, you can make the transistor wider and basically reduce its resistance, reduce the RC time. Okay. The other thing to notice here is that the resistance of the P for, the same size device, say if you have a PMOS that's 1 micron compared to an NMOS that's 1 micron, the resistance of the P is 6.51 kilo ohms to the N's 2.69 kilo ohms. So again, it shows you that the P's current is, 2.5x less. So the effective resistance for the P is sort of like, 2.5x higher. That means if you want the rise or the prop delay for, when the PMOS is turning on, so, the low to high transition to be the same as the high to low transition, you'll probably want to make the P 2.5 times wider to get the same RC delay between those two. Does that make sense where we're going here? And the strength of this approach is that, again, you do it just once, right? This R sub n, R sub p, whatever, you just do it once for the process, and then you have that number, and you can just sort of multiply that number by the width of the device you're planning to use or you have already used to get the effective resistance. So that's the effective resistance. We also talked about an effective capacitance. And the capacitance is a little bit easier. So the effective capacitance is just summing up all the capacitances at the output of that device, right? So there is the effective capacitance, say NMOS, at the output of an NMOS. Let me share my screen again. So this was the effective resistance. Now, the upshot of all this, for example, again, if you wanted to use let me talk about the capacitance, and I'll talk about what the net result is here. Sorry, let me get my ducks in a row here. Okay, over here. Okay. Okay, so those were the R's. The C is a little bit simpler. All you do is, if you were looking at the output of a CMOS, like an NMOS, right? So you're saying I have an effective R effective. So what is the C effective or R sub N for an NMOS? So this is C effective or C sub N for a NMOS. The C is just the capacitance on the drain, right? So you have a certain drain capacitance. So for example, if you look at the cross section on your device, so this would be poly, this would be oxide, this would be the drain source. So you have a capacitance here from this junction. So this capacitance per width, okay, you use as your C sub n. So again, it's a function of width, because just as a resistor, the resistance of the device drops as you make the device wider, the capacitance actually goes up as you make the device wider, because this junction, so if I look at the width is kind of going out here. I'm really bad at drawing these things, but so as I increase the width, this junction area is getting bigger and bigger, sort of linearly with the width increase. So my resistance goes down, but my capacitance goes up. So back to my table. Notice that C sub D, or the drain capacitance, is given in femtofarads per micron. Again, kind of a weird, so this is C sub D here. Hopefully you guys see my cursor. So in the case of the TSMC process, it's 1.12 femtofarads per micron of capacitance. And so this is the distance measurement is, now it's talking about femtofarads over micron as opposed to, resistance. So this says that, if I have a 10 micron, if I have a 1 micron wide transistor in this process, I multiply 1.12 by 1 micron and I end up with 1.12 femtofarads of drain capacitance. If I have a 10 micron wide device, I've multiplied the same thing by 10 microns and I end up with 11.2 femtofarads. So I end up with higher capacitance. Okay, widening up a device. And again, I use this table. So I only, again, even for the capacitance, I also have to do it once. I guess the calculation, honestly speaking, the calculation is still somewhat hokey. This is because it's not a single number as the output voltage. So let me just, this is really gets kind of complicated, but for the sake of complete disclosure, as your output is shifting, I don't know if you guys remember, but as if we're just looking at the capacitance of this junction, as the voltage on this thing changes, the capacitance is also changing. It's a reverse bias junction. So as the voltage goes up, the capacitance shrinks and vice versa. Okay, so it's not really a constant capacitance. It's still kind of an estimate. What happens, SPICE is actually recalculating this capacitance for every voltage step. So anyway, you have that value. Now, additionally, you have another thing, because remember what we're trying to do is, so let's put the whole thing together. So you have a, what are we doing on time? Oh, 8:04, okay, good. We do this. Let me talk about it here. So let's put the whole thing together. Okay, so we have, this is our inverter. And it's going to be, in most cases, driving another gate, right? So let's say it's just for the sake of discussion, it's driving another inverter. It could be another gate, and we'll get to the general case. But let's say in this case, we're driving another inverter. And so let's say we're just wondering what happens is, we're trying to estimate the fault of this node. Okay, so basically the PMOS is out of the equation and the NMOS is pulling down on this node. So what does this look like? Well, we will replace the NMOS, gets replaced with a resistance. Okay, and for the sake of this discussion, let's say it's a 10 micron wide NMOS. For whatever reason, decide to make it 10 micron. Let me just see if we get the chat. Sorry, Derek and Tunji, you guys had some questions? Sorry, so effective resistor is just a load line within the voltage range we want to test. Yeah.
Low line, although you didn't draw a low line, you were just drawing, you know, like a low line using like that minimum voltage and the maximum voltage, or the 50% voltage.
Yeah, I don't think of it as a load line. It's not the load line in that sense, because a load line would assume that you have a resistor sort of existing in series with your NMOS. So that would be a load line. What we're doing here is something really hokey. It's not like legit circuit design approach. Like a load line is a legit circuit design approach. What we're doing is we're kind of like saying, well, assume the transistor is in this single operating point where the gate is at VDD and the output is at VDD over 2. Okay, so let me see. So you're saying, okay, let's say if I was just, where the heck did I have any of these crazy drawings? So you're saying, okay, initially, let's say I'm just sitting here, right? I have my transistor is sitting where the gate is at the supply voltage and the VDD is at 0.9. At this point, there's a current coming out of the NMOS. So you're saying, what resistor value would I need to give me the same current? So what you would draw is you would draw a line here and you say, okay, this resistor value with value 1 over R being the slope, if I was just sitting here at 0.9, it would give me the right current value just at this point. And you'd say, okay, well, the other end of this line, if my input was at the 0.9 volts or the 50% point, my output was at 1.8 volts, what resistor would I need to give me exactly that current? Well, that's 1 over R1, that slope. So it's really the resistors are like, you're just coming up with this hokey thing that, hey, if I needed a resistor to give me a current voltage, the right current and voltage just at that node, what value would that resistor be? And if I had a resistor that gave me the current versus voltage just at that node, what would that be? And then I'm going to pick an average of that value. And that's what I'm going to use for my effective resistance. Because remember, it's not a load line in the sense that we're not saying we have an NMOS and a resistor on it. We're saying we are pretending like this NMOS is a resistor. And again, it's like a really cheesy estimate, but that's what we're doing. Does that make sense?
Yeah, for sure. It's similar to a load line, but I guess is what we're trying to say, because like a actual load line would have started
Yeah,
right
well,
on VDD at 0 for I, exactly.
yeah. But yeah, so, but you know, yeah, I wish it was a load line. It's like really hokey. I have no defense for this except that it just by the grace of God, it gives you a good estimate when you're doing hand calculations. But it's not like any legit analysis methodology at all. It's just a bunch of hand waving stuff. So take my word for it.
Will do.
In the end, I think what you just have, in the end, you just have to use the R sub n and C sub n from the table. That's what I would do if you're doing estimates, or whatever the process gives you. So anyway, sorry about that. But okay, so back to what we're doing. So let's say for the sake of discussion, the width of this guy is 10 micron and the length is 0.18 micron. Okay, so here, this resistor value would be R sub n divided by 10. Everybody with me? So the remember R sub n is given in terms of kilo ohms times micron. So if my transistor here is 10 microns wide, it's going to have 1/10 the resistance of a 1 micron wide device. So again, in the case of the 0.18 micron TSMC process, in a very specific case, R sub n was, I think it was 2.6 kilo ohm microns. So this would equal to 260 ohm roughly. Okay, so that would be the resistance of the N. Okay, so now, because remember, we're trying to figure out an RC time constant, now we got to start figuring out what all the different capacitances here. Well, the first thing is the capacitance of the N. And remember, the N is 10 times 10 microns. So the capacitance here is going to be C sub n times 10, because it's 10 times as wide. And I think in this process, it was 1.12 femtofarads per micron, again, in the same process. So it would equal to a 11.2 femtofarads capacitance for the N. This node, the source would also have a capacitance, the same as the drain capacitance. So I'm going to draw it. And the capacitance would be C sub n times 10, 0.2 femtofarad. But it turns out it doesn't really come into our calculations because the source for an inverter is grounded. So both sides of the source capacitor are grounded, so it doesn't really matter. Okay, so let me drag this over. So the next thing I have to worry about, and the reason I mentioned this, is I have to worry about the gate capacitance, of what I'm driving, okay? Because these also go into my RC delay calculations. So if you look at the table that we have in the book, it also gives you a C sub G, okay? And then it turns out the C sub G for the N and the P turn out to be the same because you make the gates at about the same time. So I'll have a C sub G for what I'm driving. So let's say what I'm driving is, let's say this is 10 micron wide. Let's say this is 20 micron wide. I'm driving a bigger inverter. So this ends up being C sub Gn that I'm driving is going to be 20 times C sub G. And I don't remember what that is. But I'm also driving the capacitance of the PMOS. So that ends up, also need to add the C sub GP. And because I probably made my PMOS 2.5 times bigger for getting the right ratio of N and P for resistances, this width is probably, I don't know, maybe 50 microns. and the length is 0.18 microns. So this C sub GP is 50 times C sub G, okay? And this PMOS is off, so its resistance doesn't come into it. But notice the drain is still hooked up to this node, whether the PMOS is on or not. So I also have to include the drain of the PMOS, which, you know, again, I'll probably design this PMOS to be what, 25 microns wide. So this C sub P is going to be times 25 will be the capacitance. So basically, I would end up with this RC network. So I have a single resistance. So in summary, I'll have a single resistance of, this is just on the pull down. So like I said, I can get rid of this because it's connected on both ends to ground. So it'll be 260 ohms. And then I'm going to sum up all these capacitances because they're all in parallel. I can sum all of them. So I'm just going to call that C total. So it's all of these capacitances. And that RC time constant is gonna basically give me the I'm claiming that will give me a good, accurate, reasonably accurate delay for the prop delay fall with this really simple RC network. So that's kind of the net. Okay. So I hesitate to ask this, but so I'm going to stop here. And we're going to talk about the general case in the next class. Any questions? I know lots of hokey stuff in this class. I always dread this lecture.
I have no questions.
Okay. Okay, guys. Well, have a good weekend. Good luck on the project. And I should be around this weekend, Sunday. Well, no, I should be all around. So just send me an email if you guys run into issues with your project. Good luck. Hopefully it'll make some of this stuff make sense.
Thank you, Professor.
Okay. Thanks, guys. Take care.
Right.
Bye.